Okay. So I wasn't lying, you're gonna like this section. At least I do, I love this section. 3.6 is on L'Hopital's rule. Let me spell it right. So sometimes we'll have like the limit as x approaches a. Of some function f of x over g of x. And we were doing this in chapter 1 and 2, we often saw. This can lead to an indeterminate answer. Indeterminate. Indeterminate. For example, a couple times we saw we would get like 0 over 0. That's not a division sign, that is 0 over 0. Or we could get like infinity over infinity. This is where L'Hopital had his genius. There's another version, it looks kind of funny. If we had f of x times g of x, it could look like 0 times infinity. But remember, no, these are always approaching, when we're doing limits, we're approaching. So like this is approaching 0. And this is approaching also, and which one's winning? Like something times infinity is gonna blow up, but something times 0 goes to 0. So like what form is winning? That's the idea here. Another way of looking at this one though is like this is 0. Divided by 1 over infinity kind of thing. That's doing the same thing, which would be 0 over 0. So that's really just another way of writing this one. These two are versions of this. You'll see that we'll eventually expand it to other things, but L'Hopital, it looks like the word hospital without the S. L'Hopital in his geniusness found out that the limit as x approaches a of f of x g over gx is going to equal the limit as x approaches a over or time f prime of x over g prime of x, assuming this limit exists. Or is plus or minus infinity. That's a result that works as well. That's not actually a limit, that's limitless. So two important things to note. Important. A. This is not the quotient rule. You do the top and bottom derivatives separately. feet. Sometimes you have to do it more than once. And see. It's good practice. To show. That you are. For a lack of a better word, activating L'Hopital's rule. And an easy way of doing that is. I'm writing what I had just above. But as you do it, above the equal sign. Put in like L apostrophe H or something like that. Maybe with an arrow. Showing that you're doing L'Hopital's as you switch, because otherwise they look different and. You might not recognize later on what you were doing. I may not know what the hell you're doing, it's like I will recognize it on this test, but you might do it on a later test and it might. And you might do it for no reason, and I'm not gonna know what the hell you're doing if you don't indicate you were trying to do L'Hopital's. And I guess there's a fourth one that's pretty important. You must show it's an indeterminate form first. Before using it. Is ready to do a bunch of examples? But no, people are still ready. Other versions that show up. So like, we're looking for 0/0. Infinity over infinity. Infinity minus infinity is one that requires looking at. 0 to the 0 power. Infinity to the 0 power. And 1 to the infinity power. The reason why for the other ones, these could be different infinities. Which seems silly. I think it's ridiculous, but. Pure mathematicians, theoretical mathematicians. Argue that there are different levels of infinity. On both of these, a zero exponent means 1. So what's winning? Is the number going to 1 or is the number going to 0 or infinity? So there's a conflict there, which thing is winning, the base or the exponent? And this one, same idea. 1 to any power is 1, but like 1.0001 to infinity is gonna blow up to infinity. So like which is going faster? Which is winning, the 1 or the infinity? There's several reasons to bring this up, but that some of these don't show up very often. Example number 1. The limit as x approaches 1. Of x to the a minus 1 over x to the b minus 1. If I plug that in, I've got 1 to the a minus 1 over 1 to the b minus 1. But anything 1 to any power is just 1. 1 minus 1 over 1 minus 1 is 0 over 0. It's in indeterminate form. So we will trigger a L'Hopital event. You always want to keep writing down the limit until you actually evaluate at the limit. What is the derivative of the top?
Ax, a minus 1.
Yeah. Bottom,
Same thing for b.
and now when I evaluate. I have ax to the 1 minus 1 over bx to the 1 minus 1. Which is just a times b. X to the 0 is 1. Or those two cancel out, we're just left with a over b. Which means. The limit as x approaches a of x to the a minus 1 over x to the b minus 1 is a over b. Ready for another?
So I'm confused, why do we plug in 1 over a and b in the exponents?
Where?
In the exponents, like plugging in 1 minus 1 for both.
I'm doing the wrong shit there. I totally did the wrong shit there. A to the 1 a minus 1 over b to the 1 b minus 1, thank you. I totally fucked that up. Plugged it in the wrong goddamn thing. But still, 1 to any power is 1. And that's the same for top and bottom. Good catch. It's funny, I even have it written down correctly in my notes, just fucking. Checking to see if you're paying attention, that's all. Right?
So you plugged in 1 for x?
Yeah,
Okay.
and that's what we were supposed to do. Cause we're doing the limit as X approaches one. That was me just fucking up the first go around. Alright, we're gonna do the limit as X approaches 0 of X plus tangent X over sine X. Why don't you guys give this a try, see what you come up with.
Just make sure. Just, so, sure.
Yeah, well. Let's see. Excuse me. This is- so basically, it's just- Here. See. So obviously.
So once you put it in one, let's do it, then you can use.
Mhm. So the derivative of the top and bottom, but we're doing them separately,
Yes.
okay.
What's the first step here?
To prove that it's indeterminate.
That is the first step, we gotta show that we're using L'Hopital for a reason. So 0 plus tangent 0 over sine 0. What is tangent 0?
Zero.
0. If you need to think about it, tangent is sine over cosine. And that would be 0 over 1. Which is 0. Sine 0 is 0, so we do have an indeterminate form. So we'll use L'Hopital rule. What's the derivative of the top? 1 plus secant squared x. It's the derivative of the bottom. Cosine x. Now, I don't know about you, but I may not remember how secant works. I'm gonna rewrite the secant as 1 plus 1 over cosine squared x. Because I know what cosine and sine values are fairly easy. Secant, I'm all I get, what? I gotta grab a calculator. But if I plug this shit in now, I get 1 plus 1 over cosine of 0 squared. Over cosine of 0. Which is 2 over 1. I wrote theta there, that should say 0. Cosine of 0 is 1, so we got 1 plus 1 on top, 1 on bottom, 2 over 1 is 2. Remember, I'm gonna take us back there real quick. Remember when we had to do like limit as x went to 0 of sine x over x? We had to walk through some big bunch of bullshit with the squeeze theorem and all that. Doing it here gets you the answer pretty quickly. We can see this is 0 over 0. So it triggers L'Hopital. Just gets us a 1. So that whole squeeze theorem thing is now super easy. We also had. I wanna say we looked at 1 minus cosine x over x. And that ends up being 0 over 0. And so if we do L'Hopital on this. We get negative sine x over 1. Which is just 0. And we had to do a bunch of shit to derive those using fucking squeeze theorem, and there's a way to do it with triangles, there's a lot of ways to do it. But then you use L'Hopital's rule, and like this shit's super easy. So these are things we did the long way before. I got more fun ones, don't you worry. This isn't too bad, is it? I told you would like it. It's not like introducing anything that's different, not something you haven't learned already. Just a way to apply it differently. You're just still doing derivatives. Anyone need that up longer? Alright, on where we go. Limit as x goes to 0. Sine x minus x. Over x cubed. So if we put in 0, we got sine 0 minus 0 over 0 cubed. This is 0 over 0. That will trigger a L'Hopital. What's the derivative of the top here? Cosine x minus 1 over 3x squared. So let's put in our 0, we got cosine 0 minus 1 over 3 times 0 squared. 1 minus 1 over 0, this is still 0 over 0. So let's do it again. What's the derivative of the top now? Negative sine x. What's the derivative of the bottom? 6x. Oh, look at this motherfucker. Negative sine 0 over 6 times 0 is again 0 over 0. But that's in an indeterminate form, so again. What's the top? Negative cosine x. What's the bottom? 6. And now we stick in 0. And we get negative 1 over 6. Which means going all the way back up to the top. Limit as x goes to 0 of sine x minus x over x cubed is negative 1/6. If one side is a polynomial, it'll eventually drop out. If you have to keep taking derivatives and one of them is a polynomial, just x to a power, eventually that fucking thing loses. Cause you'll take a derivative down to where it gets down to a constant like this. Sometimes it takes a while.
Bread and sliced cheese, Hefe.
What?
I said bread and sliced cheese.
That is. Some fucking good shit. Yeah, otherwise you're like, I don't know how to fucking do that. Got an answer, but I didn't know how to do it. Let's try this one, limit as x goes to 0. We're gonna say from the positive side because one of these does not exist from the negative side. Natural log of x does not have a 0, can't do 0. And if I try to evaluate, I've got sine of 0 times natural log of 0, and this is 0 times negative infinity. And one of them is not 0 and one of them is not infinity, but they're both going to their competing forces. So. What can we do? This is not in L'Hopital's form. But it's similar to what L'Hopital's process is. Can I write this as a fraction? Well, putting it over 1 doesn't change anything. I do the derivative of the bottom, I'm gonna get a 0 on bottom, it's just gonna fuck everything up. We can do 1 as a negative exponent. So like sine x could be rewritten as 1 over 1 sine x. Like moving it to the bottom and using a negative exponent. Like this is saying 1 over sine x to the negative 1. But that looks like that. But what is this? That's cosecant, right? Let's try that. That will give us what we're looking for. It gives us a fraction. And I'm gonna say L'Hopital. I didn't give myself room to right to the left like I normally do. I got all excited. I haven't done L'Hopital yet. Here we go. That's the L'Hopital. What's the derivative of the natural log of x? Top is 1/x. What about cosecant x? With a negative. I don't know if you said the negative, but I heard you say cosecant cotangent. Good. Alright, so we got check, we've got. 1/0 here, and we've got. Negative cosecant 0, cotangent 0. What the hell is that? Cosecant is 1/, I'm looking at the bottom right now. Bottom is 1/sine. And then cotangent is cosine over sine. And if I put in 0, and then we got a negative. If I put in 0. I'm getting some shit again. I'm getting a number over 0, which is making the bottom go to infinity. And the top's infinity also. So this is an indeterminate form. That's okay. We'll use that. To do another L'Hopital. So I'm gonna rewrite that as x to the -1 right there. And you know what? This might be a little bit easier if we clean this shit up a little bit. Before we do that, let's clean that up. We have 1/x. Times cosine, negative cosine x over sine squared x. So if we clear fractions. Let's multiply top and bottom by sine squared x over cosine x. And we get sine squared x over x cosine x. And that was the limit as x goes to 0. And now we'll trigger L'Hopital. To do this, you gotta remember that the top is sine x squared. That's what sine squared x means. So we got a chain rule. On the top, we bring the power down and leave that alone. And then we take the derivative of the inside, which is cosine x. On the bottom, we have a product rule. So we'll do the derivative of the first, which is 1 times cosine x. Plus the first times the derivative of the second, which would be negative sine x. And this is still limit as x goes to 0. And when we evaluate this, we get 2 times 0 times 1 over 1 plus 0 times 0. 0 over 1 is 0. We got an answer. So we had 0 times infinity in the beginning, the 0, 1. That's the final answer. Alright, we got two more. See if we can get through them. Next example, limit as x goes to 1. 1 over natural log of x. Minus 1 over x minus 1. If we plug in 1, we've got 1 over natural log of 1. Minus 1 over 1 minus 1. This is 1 over 0 minus 1 over 0, which is infinity minus infinity. So this does meet a L'Hopital thing, but we're not in L'Hopital form, because we got two different fractions. Problem right now is we got two different fractions, so let's get a common denominator. I'll multiply the first one by x minus 1 over x minus 1. And I'll multiply the second one by natural log of x. So we put them together. We get x minus 1 minus natural log of x. Over natural log of x times x minus 1. If you evaluate here, you get 0 over 0, so this is still L'Hopital. So we're gonna take the derivative of that top. And I get 1 minus 1 over x. And on the bottom, I have a product rule. The derivative of the first times the second. Plus the first times the derivative of the second, but the derivative of the second is 1. I'm just gonna clean up the top and bottom a little bit by distributing. 1 over x times x is 1. 1 over x times -1 is minus 1 over x. And then we've got plus natural log of x. Wait, I just changed that to 0. That's an x approaching 1 here. This unfortunately does still give us 0 over 0. So both top and bottom have a -1 over x, that's the same as -x to the -1. When we do our L'Hopital here, it's easier to look at that. So the derivative of 1 is 0. To take a derivative of -1 over x, we're looking at the derivative of that. We bring the power down and lower the power by 1, x to the -2. That's gonna happen on bottom as well, we're gonna have x to the -2. Plus the derivative of natural log of x is 1 over x. And that's getting confusing, so like, let's multiply by x squared over x squared. We can do that because x is going to 1, so we're multiplying by a legitimate value. This is not doing L'Hopital, we're just cleaning things up a little bit here. And I get X to the 0 on top and then x to the 0 plus. X to the first power on bottom. And now when we evaluate. We get 1/1 plus 1. Is 1/2. So infinity minus infinity is 1/2. At least in this circumstance. I've got one more example, but we don't have time to do it. Maybe I'll record a video of it later, or maybe we'll do it on Thursday. Thursday, yeah, Thursday. Have a good day, guys. Yeah, GTFO. So test is not next week, it's the following week. We're gonna start chapter 4 on Thursday, and then we'll do, next week will be. Continuing chapter 4, and the first day we'll do the group practice test. Maybe we'll do the group practice test on, I don't know, one of the days next week. But the following week, I'll have the syllabus change today. Just keep that in mind. Peace.